Yeah. And the last talk of the day is by Swagato. He's going to talk about Fourier sparsity, Fourier dimension and sparsity.
So thanks, Meena, and thanks to the organizers for organizing this event and giving me an opportunity to present this work. So the title of the talk is Fourier dimension and sparsity. So let's begin. Let me begin by defining these terms. So we'll be looking at Boolean functions. So we know what Boolean functions are. They are functions that take in n bits and output 1 bit. So instead of the more conventional 0, 1, we'll think of the domain as plus minus 1 to the n, and the range as plus minus 1. And we'll think of the range as a subset of reals, and we'll often subject them to real number operations, like addition, multiplication, etc. So we'll actually take two views of the domain. Sometimes we'll view the domain as the vector space, n-dimensional vector space f2 to the n over the field f2. And whenever we think of it as plus minus 1 to the n, we'll think of it as a subset of r to the n. And the range is always plus minus 1 to the r. So, and to switch between the two views, the minus 1 in plus minus 1 is identified with 1 in f2, and plus 1 in plus minus 1 is identified with 0 in f2. So it's just a natural isomorphism between the two groups, minus 1 plus 1 under multiplication and 0, 1 under modulo 2 addition. So it's well known that for every Boolean function, there is a multilinear polynomial with real coefficients such that fx is equal. So whenever plus minus 1 values are substituted, the polynomial evaluates exactly to the function at all points on plus minus 1 to the n. So actually, it's true even for arbitrary value, even for real value, for that matter, even the range when the range is complex. But we'll mostly look at functions where the range is plus minus 1. So this is one example. This is the 2-input AND function. So minus 1 stands for the logical true, and plus 1 stands for the logical false. So it's easy to verify that whenever x1 and x2 both are minus 1, the polynomial evaluates to plus 1, and for all other values, the polynomial evaluates to whenever x1 and x2 is minus 1, the polynomial evaluates to minus 1, and for all other assignments, it evaluates to plus 1. So the monomials, so it's a multilinear polynomial, so every monomial is a product of some of the variables. So the variables are plus minus 1, so the product is also plus minus 1. So product is plus 1 if and only if there are even number of minus 1s among the variables. So these are exactly, so for every subset of 1 to n, I have a monomial which is the product of xi's where the index lies in that set, and it's equal to, so it's actually the plus minus 1 version of the parity. So parities can also be thought of as linear functionals, linear functions from the field f2 to the n to f2. So the the set of all linear functionals under the natural addition they also form a vector space over the same field, and that's called the dual vector space f2 to the n hat over f2, and it's actually isomorphic to the original or to f2 to the n. So from now on, we'll identify the monomials as vectors in this dual space f2 to the n. So we'll identify the monomials as linear functionals. Okay, so the Fourier, the polynomial in the earlier slide, that's the Fourier expansion of a Boolean function. So Fourier support is just the set of non-zero monomials. In other words, the set of monomials that feature in the Fourier expansion of the function. And the Fourier sparsity is just the number of terms in the Fourier expansion of a function. Fourier dimension is, so as we have seen, the monomials can be thought of as vectors in f2 to the n hat, and they come from some vector space. So I can talk about their whether they are linearly independent and so on. So the Fourier dimension of a Boolean function is just take the span of the Fourier support of f hat by treating the monomials as vectors in f2 to the n hat, and take so you get a subspace and take the dimension of that subspace. Any question at this point?
Sorry.
Yeah.
What was f2 to the n hat? What was the hat?
So it's actually, f2 to the n hat is the set of all linear functions from f2 to the n to f2, and the monomials can be thought of as members of this set. So now the question we'll ask is how do these two measures, dimension and sparsity, how do they relate to each other? So this relationship is immediate from the definitions. So dimension is of course upper bounded by sparsity, because dimension is the number of linearly independent vectors, which is of course upper bounded by the total number of vectors. And it's lower bounded by log sparsity to the base 2 because it's an F2 space. So if V1 and V1 to VL are L vectors, then the total number of linear combinations of V1 to VL, the number is at most 2 to the L. So any set must have at least log of, so any set of size, let's say S, must have at least log 2 as many linearly independent vector in it. So can we say something more? So the lower bound is, so is there a function which, so let's look at the inequalities. So is there a function for which for instance, the second inequality holds with equality? This is the question that we first ask. Yeah, so for indicators, so let's say for the n variable AND function, one can show that all the Fourier coefficients, all the monomials featured in the Fourier expansion, so there are 2 to the n of them. And the dimension of the space is of course n, it's f2 to the n, so the n dimensional space. So sparsity is, so dimension is exactly equal to log of sparsity. So how about the upper bound? So dimension is of course smaller than or equal to the sparsity of f. So so the tightest example known is what is called the address function. It's a function of half log s plus square root of s variables. So there are half log s variables. The x part refers to the first half log s bits, and it actually so it serves as an index for one of the yi's. So there are root s many yi's, and then you read the value of the corresponding yi, and that is the value of the function. So this is the address function. So one can show that sparsity of the function is s, because there is a decision tree of depth like half log s. You just read the x variables and then read the corresponding y. And yeah, you can immediately, from that decision tree, you can immediately construct the polynomial and see that it has at most s many monomials. The dimension is of course at most, so dimension is root, so there are approximately root s variables, and one can show that the dimension is omega of root s. I think all the y variables, all those monomials, all those y1, y2, up to ys or y root s, they all feature in the Fourier expansion. So the dimension is at least omega of square root of s. So now the question is there a tighter example? Is there another function for which the two quantities are closer, or can we improve the upper bound? This is the question that we are going to ask. So now, of course, all we have said is true for arbitrary real valued function, or even for that matter complex valued function, and all these definitions, sparsity, dimension, etc., continue to make sense even for real valued function. And we can ask this question even for real valued function, except for the fact that it becomes, means of course I can just write a polynomial supported on a linearly independent set of monomials, and for which the inequality holds tightly, the inequality. But then the range of the function won't be Boolean necessarily, it will arbitrate to real values. I want the polynomial to evaluate to plus minus 1 values everywhere. So what happens if I impose this restriction that the function has to evaluate to plus minus 1 everywhere in the domain? Can we say something more? So so this is just the restatement of the question. So let's first begin by showing that the upper bound cannot hold with equality at least. So all the monomials cannot be linearly independent. So what happens? So let's say the function looks like this. Let's say M1 to MD are some linearly independent monomials. So I think without loss of generality, you can think of them as variables. It doesn't. So let's say they have these real coefficients in front of them. Yeah. So yeah. So think of M1 to MT. Think of Mi as Xi. So now I ask the question: can I choose coefficients Ci's, and also I require you to choose non-zero values for all the Ci, such that the function always evaluates to plus minus 1. Of course, so it's easy to see that it's no. Any such function evaluates to at least d plus 1 distinct values when on the hypercube. So the d plus 1 is attained when, let's say, it's the sum of the x, when all the Ci's are the same. Xt. So if D is even, then if I cycle over the inputs to x1 to xt, f takes all the even integers between minus d to plus d. So there are d plus 1 many possibilities, I think. So and in general, this is the tight example. So in general, any such polynomial, which is a linear combination of linearly independent monomials. So unless d is equal to 1, I cannot have such a Boolean function. Is it okay? Or, so at least the dimension is upper bounded by sparsity minus 1. It cannot be all the way up to sparsity. Yeah. So can we get something more out of this approach? So if you do it a little more carefully, so let me do it here. So let's say in the Fourier expansion there are d independent monomials, and we saw that a linear combination of d independent monomials cannot be Boolean, and it evaluates to at least d plus 1 distinct values. So you must have more terms that make sure that the polynomial evaluates to plus minus 1 values everywhere. So let's say, is there a dust? Let's say these are d plus 1 points in the domain of the function on which this portion evaluates to distinct values. Now look at the values of the function on these d plus 1 points. So these are of course Boolean valued points because the function is a Boolean function, and at least d plus 1 over 2 of them will be same. Let's say d plus 1 by 2 of them are plus 1s. So in all these courses, on all these points, the remaining portion of the function that we have must evaluate to 1 minus. So let's give it a name. Let's say p. So that px plus this becomes 1, and as px takes d plus 1 distinct values, this also takes d plus 1 distinct values. So there must be at least log 2 d plus 1 by 2 many monomials in this portion. So you get slightly better upper bound, slightly better lower bound of dimension plus log of dimension plus 1 by 2 by this. So the question is, can we say more? So prior to this, the best known lower bound on sparsity was by Gavinsky, Kirchner, Wolf, and Samorodnitsky, and they proved a log dimension lower bound on sparsity. So this is the main result of this talk. So actually, the upper bound can be improved a lot, and the dimension, one can show that the dimension is order of square root of s log s. So there is a couple of comments here. So the initial analysis proved order of s to the 2/3. So later Avishai Tal, who is a PhD student in Weizmann, so he observed that the analysis can be tightened to square root of s log s. And in the light of the address function, as that we saw before, it is optimal after log factor because there is a function for which dimension is omega of square root of s. How much?
Yeah, another 10 minutes.
Another 10 minutes. So let me just outline our approach briefly. So we look at, to derive this upper bound, we look at parity decision tree. So what is a parity decision tree so parity decision tree is an algorithm for computing a function which goes, so the algorithm makes parity queries, means, so it has access to a, let's say, oracle, and it can make queries, parity queries, like what is parity of x1 XOR x5 XOR x6, and the oracle replies back by plus 1 or minus 1. And it makes such parity queries and eventually outputs the value of the function. So this is a parity decision tree, and the evaluation can be naturally represented by a tree. For example, let's say this is our function f, and x3 XOR x4. So the tree can first query x1 XOR x2. If it is 0, then we know that the function is 0. If it is 1, then we query the next parity x3 XOR x4. Of course, if this is 0, we know it's 0, and if it's 1, we know the function is 1. So the leaves of the tree are labeled by, so I should have probably said 0 plus minus 1 instead of 0. Yeah. So the leaves of the parity decision trees are are labeled by the value of the function on the inputs that lead to that leaf. So typically, at a particular point in time, the choice of the query will depend on the responses to the previous queries. For instance, here we choose to query x3 XOR x4 only when the response to the previous query was 1. Had the response been 0, we wouldn't have queried it. We would have known that the function evaluates to 0. So such trees are called adaptive trees. In general, typically the trees will be adaptive, means the queries will depend on the responses to the previous queries. So if the choice of the query, choices of the queries don't depend on the previous queries, responses to the previous queries, we will call the tree. So the tree is called a non-adaptive tree. Yeah. So this is what I said. And the objective is to minimize on the number of queries. So I don't care about any other form of any other computation. In the worst case, number of queries. So non-adaptive decision trees, yeah. So this quantity NADT parity F is the minimum number of queries made by any non-adaptive parity decision tree computing F. So this proposition is actually quite simple observation, that the non-adaptive parity decision tree of F is equal to the Fourier dimension. So one way is simple. So if the Fourier dimension is, let's say, D, then there are D linearly independent monomials in the Fourier expansion. You query all of them and you know the function, because you can just evaluate you know the values of all other monomials because they are linear combinations of these monomials, and you know the value of the function. You can just evaluate the polynomial. The other direction is also quite easy, which is what we need for the upper bound. But yeah, the one-line explanation is that without loss of generality, the independent monomials can be thought of as variables. If they are not, you apply an affine transformation on the domain and make them variables. Yeah. And under affine transformation, all these measures are preserved, sparsity, dimension, etc. So this offers a possible approach to upper bound dimension F, exhibit a shallow decision tree, not a parity decision tree for F. So how much time do I have? Sorry.
6 minutes. 7 minutes.
Yeah. Okay. Let me see. So what we do is, so already in the literature there is a parity decision tree of depth square root of S. So this is a result by, I think, Amit Shpilka, Ben Lee Wok, and I think Avishai Tal. Yeah. So they show that there is a parity decision tree. Let's say parity. So for every function f of sparsity S, there is a parity decision tree of depth order square root of S that computes. So that tree is an adaptive tree. So what we do is we look closely at that tree and try and make it non-adaptive, and by incurring a blow up of a factor of log S in the depth, and that proves the theorem. So that their parity decision tree goes as follows. The first step in that construction is that they prove that if a function has sparsity S, there is a large subspace in F2 to the n of codimension. So there is a large subspace. codimension like order of square root of S, large subspace, let's say V. So affine subspace, such that the function is constant on that subspace. Let's say 1, no, constant, okay. So any such any codimension is the solution space of some linear constant. So any codimension of, any affine subspace of codimension square root of S is the solution space of some linear constants, let's say gamma 1 x equal to 1, gamma 2 x equal to minus 0 or minus 0, and so on. Gamma t, where t is like order of square root of S. Yeah, so this suggests a natural parity decision tree, which is the first step is query these parities. So these are parities, these are the linear forms that define the space. So query gamma 1 to gamma t. So you have a tree of depth t. So these leaves corresponding to the different responses that you get, and one of this theorem tells you that one of them is a constant. So let's say this one is a constant, and others will still be functions restricted to the corresponding. So if the responses match with these bits 1, 0, etc., then we know that the restricted function is a constant. And for every other response, I get some other function on the restricted affine subspace. So now the second step is showing that all these functions, the sparsity of all these functions has gone down by a factor of at least 2. Okay. And you keep doing it. So you will go on for log s many steps. So yeah, so here you will make square root of S queries. So in the next step, you will make square root of S over 2 queries. And if you add the queries, it's a geometric sum, which adds up to order of square root of S. So this is so note that this is an adaptive tree, because here the queries I pick, the queries I choose, so the parities I choose to query depend on the fact that I am here, which in turn depend on the responses I got that led me here. So to turn it to a non-adaptive tree, I must ensure that the same parity is queried at all the nodes in a particular level. So what we show is here at this point there is a choice of parity such that at this point we can compute a small number of parities such that when we query the function on those parities, query those parities everywhere on all the leaves, the restricted function reduce the sparsities of the restricted functions also fall by. So we won't be able to show that they fall by a factor of 2, but we'll show that it falls significantly and so on. So the existence of these, it won't be S, it will be something else maybe, T. So the existence of these parities are argued with a probabilistic method. So we'll show that a random function will have this property that, and that argument, and in that argument we use this what is called the Boolean uncertainty principle. Yeah. What else? Yeah, I think that's all. And one more comment maybe. So this theorem is not believed to be tight, and it is believed that this bound can be improved to polylog of S. And if you improve this theorem, you can shave off the log factor and get optimal. Thank
you. Any questions, comments? The end of the day is difficult to get comments. Okay, so.
What was your question?
Huh?
What was your question?